say these are the molecules or atoms. These are the molecules or atoms in the material. Okay? These are the atoms, molecule in the material. Okay? So these will be oriented somehow like this. These will be oriented. Okay? Orientation was different before the application of the field. We are going to apply the field to this. When I apply the field to this, what is going to happen is these are going to align in one direction. These all will align in one direction. So this is called as the polarization. It is called as the polarization. These will align in a direction. This process itself is polarization, and this material is dielectric material. It is like that. Okay, so these are many atoms. What I did, I have applied the field to these things. Okay, positive or negative or whatever. So I have applied the field. Let us say this is the atom X, fine, and this is A1, this is B1. Okay, the same way this is A2, this is uh, this is B2. Okay, and so on. So it will be, there will be millions of atoms or millions of molecules inside the material. So what we have considered, only 5 6 atoms or the molecules we have considered for an for our consideration for example. Okay, so here the distance between, this is called as intermolecular or interatomic distance, is D. So this is the interatomic distance D, and I consider only one line of that material. That one line of material is called as one dimension. This is one dimension. Okay, so one dimension array of atoms are considered. Okay, for make it very simple to construct the equation, first we have to go with the simple things. So simplest thing is to consider the one dimensional atomic array. So when I consider like this, so in the last class I told that this is the external field. E is the external field which we are applying to this. So this, whatever the positive and negative we are applying, it is external field to the material we are applying. Right? I want the field at this point. At this point, that means I need the internal field, that is called as EI is the internal field. What happens? The field acting on this is also there. External field is acting on this point, at this point, right? And the field due to the surrounding atoms also there. There are two fields acting on this X atom. There are two fields which are acting on atom X or a molecule X, right? So there are two fields. One is external field which is acting on this, and there is the field due to A2, field due to B2. These all will be having individual fields. Okay, because this is positive, this is negative. We have considered this is a dipole. Okay, so field due to this dipole is influencing on this. This is influencing on this. So like that, how many atoms are there? All the atoms have the collectively, right, the effective field on this. So that what happens is we have internal field. EI represents internal field is equal to, this is external field, external field. Okay, then the field due to surrounding dipoles. Fine. So that at this point we have the extra field. This is the external field. Okay, similarly with this atom, when we consider the field at this point, this atom will be influencing on this atom, right? So that this is not for this point. For all the atoms, if I consider the same analogy, then this is true. And this internal field for one dimension, you should remember I am considering the one dimensional array. That one dimensional array internal field is given as E divided by 1 minus 1.2 alpha E divided by pi epsilon naught d cube. is the equation for that. It is the equation for this. Okay, right. So don't bother about this equation. Fine, it is just the we are just mentioning this equation. Fine. Okay, this is just to mention the equation. It is just to mention the equation. Then there will not be any question on this. Just they'll ask the internal field, what is the internal field, and explanation for that. Okay, so this is for one dimensional array. Okay, and now if I consider the three-dimensional array for 3 dimensions, I have to consider the material. Okay, whole material. There will be another line here. There will be another line there. There will be upper lines like that. There will be so many lines. Crystal structure will be there. For that to apply, what we have is for 3 dimension. It is called as a 3 dimension. Okay, so for the whole material, the equation, that is the internal field, is given as it is EI is equal to E plus gamma divided by epsilon naught into P. So this is the equation for the internal fields in the bulk material. We call it as a bulk material. Okay, till now I considered only single diamond, single line, that is the array. Now I consider the bulk material. So this is the equation for that, and it is also called as the Lorentz field. It is called as Lorentz field. In the bulk material, it is called as the Lorentz field, where P is what? P is polarization. Polarization. It is the polarization. Okay, and this gamma is the proportionality constant. It is the constant. Okay, it's gamma is proportionality constant. It is given as 1 divided by 3 for the internal fields. Okay, and remaining all have the uh, usual meaning. This is the interplanar or interatomic distance, and this is polarizability of the due to the electrons. This is the polarizability, and this is the external field which is applied. Okay, here it is external field applied, polarization epsilon naught, and this is the constant gamma. Fine. So to take an example of a cubic lattice, if I consider for the cubic lattice, for cubic lattice, that is EI is equal to, okay, cubic lattice. For cubic lattice, internal field or the Lorentz field is, this is P divided by 3 epsilon naught, right? So this is the internal fields. So mainly we have to remember this only one equation, because I'm going to use this equation, Mossotti equation. This is the Clausius Mossotti equation. Okay. So here this, I'll write the equation. The equation is like this: epsilon r minus 1 divided by epsilon r plus 2 is equal to n epsilon e 3 epsilon naught. This we are going to prove. Okay, quite easy equation. This Clausius Mossotti equation. Clausius and Mossotti are scientists. They found this relation. This is very important relation, right? From this is number of atoms, polarizability, epsilon naught, epsilon r. Okay, this is a relation between these all things, and we have some ratio here and some ratio over in the right hand side. Okay, which is very useful. Now we will start deriving this equation. Okay, this is the last derivation of this module. This is last derivation I'm going to solve. Right? If n is the number of atoms, we'll start deriving this. If n, what is n? N is, it is the number of atoms. Okay, it means concentration of atoms, number of atoms per unit volume. Okay, this is the number of atoms. Then mu, what is mu? Motive mu is, it is dipole moment, or you can say atomic dipole moment. Atomic dipole moment. Fine. Then this is a dipole moment and this is number of atoms. If I multiply these two, then what do I get? I will get dipole moment per unit volume, isn't it? So this is number of atoms, this is the dipole moment, then the dipole moment per unit volume. Therefore, the dipole moment per unit volume, okay, dipole moment per unit volume is equal to, it is n into mu. This is equation number 1. Fine. Now we can write this dipole moment in other words. We can write this dipole moment as polarizability into internal fields. This is the equation number 2. We can write in other words like this. This is the equation. So that let us substitute this mu in equation number 1, so that this uh, dipole moment will become dipole moment per unit volume. What is dipole moment per unit volume? Dipole moment per unit volume is, it is polarization. Okay, dipole moment per unit volume is, it is nothing but polarization. Polarization is, equation will become n, substitute instead of mu, it is alpha e into ei. Fine. Next, we know that in the beginning of the chapter I have given you a small equation about the polarization. We know that the polarization P is equal to epsilon naught epsilon r minus 1 into E. This is the equation for the polarization. Okay, so what happens is E is equal to what? E is equal to, it is P divided by epsilon naught epsilon r minus 1. Okay, let us say this is equation number 4. I will take it as 4. Okay, so this is the polarization. This is n alpha e into E. That means this is equal to P. Okay, this I'll take it as equation number 3. This is also P, right? And this is also P. And from here I can take this E. Ei also can be extracted from that. So when you extract Ei, what happens? Ei is equal to, from this equation, if I write Ei is equal to, it will be P divided by, n epsilon E. Okay, so we have this E, we have this Ei now in this equation. Okay, internal field, equation for the internal field. Just now I have solved that equation for internal field. Internal field is given as, okay, I gave you for the 3-dimensional internal field, Ei equation is given as Ei is equal to E plus gamma divided by epsilon naught into P. I told you to remember this, and I told you to remember this because we are going to use in this equation. Okay, this is equation number 5. So what all things we have? We have this E. E is here. Ei. Ei also we found. Let us substitute value of Ei and E. Substituting equations of Ei and E. What is Ei? Ei is nothing but, it is P divided by n epsilon E is equal to, what is E? E is P divided by epsilon naught epsilon r minus 1, fine, plus gamma divided by epsilon naught into P. So this P and P will get cancelled. I remain with this equation. Let us see what is that equation I remain with. Fine. So what I remain with is 1 divided by n epsilon E is equal to 1 divided by epsilon naught epsilon r minus 1 plus 1 divided by, gamma divided by epsilon naught. Fine. So I'll take this epsilon naught out, 1 divided by epsilon naught. What I remain with is 1 divided by epsilon r minus 1 plus 1 divided by gamma divided by only gamma. Okay, only gamma is remaining here. Fine. What is the value of gamma? Gamma value is 1 divided by 3. Already I have given that. Gamma value is 1 divided by 3. It's a constant for the bulk material, proportionality constant. So I'll take this epsilon naught to this side. So this is epsilon naught divided by n epsilon e is equal to, okay, substituting the value of this, what I'll get is it will be 1 divided by 3. 1 divided by epsilon r minus 1 plus 1 by 3 is this. So take the LCM, it will be 3 epsilon r minus 1. Okay, so it will be 3 plus epsilon r minus 1. What I get is, I'll get this epsilon r plus 2, epsilon r, plus 2 divided by 3 epsilon r minus 1. Okay, this is epsilon naught n epsilon e. So have I reached the final answer? The final answer I wanted to get is this. This is the final answer. We have to rearrange the equation and we should get that equation. Okay, so how to get that? Take this this 3 this side so that it will be done. Okay, so what I want is epsilon r minus 1 divided by epsilon r plus 2 is equal to, it goes here, n epsilon e, fine, n epsilon e divided by it is 3 epsilon naught. So this is called as Clausius Mossotti equation. Just I have rearranged the terms and I got the equation. Right? Any doubts here? Because why we have to write in this manner only? Because we have the epsilon r terms on side and the remaining terms on the side. Okay? Here I can find out this epsilon e by knowing other things. Other things are constant for that all the material, and n will be constant for that particular material. Okay, n is the atoms per unit volume. Okay, I'll just revise this how we started, what we wanted to prove. We wanted to prove this Clausius-Mossotti equation. This is called as Clausius-Mossotti equation. They found this equation useful relation. Okay, we started with n. N is what? N is the number of atoms per unit volume. Mu is the atomic dipole moment. Mu is atomic dipole moment. And we can write atomic dipole moment in the form of dipole moment per unit volume is, when I multiply dipole moment per unit volume, I'll get. Okay, and this dipole moment per unit volume is nothing but what? It's a polarization. This polarization. We can write this mu, in other words. So here it comes. We should remember this equation. First equation we have to remember. Okay, this mu is equal to epsilon e into ei. Then this is nothing but polarization. Polarization is given as, we have to substitute the value of this mu in this equation, so that n epsilon e, then ei, that is nothing but p. Okay, we have to take out this ei from this. We have to take out means p divided by, it will be p divided by n epsilon e. We know that this equation, okay, this is the relation between polarization and electric field, external electric field, and these are the constants. So from this equation I can extract value of E. Value of E is this. This is the value of E is equal to, I just have taken this in the denominator. So I can extract this EI from this equation. EI is equal to P divided by N epsilon E. So internal field equation, this you are going to remember. This is the important equation. So in this equation, we are going to substitute the value of EI, value of E, value of ai is this, value of e is this, p all p's will get cancelled, I remain with this equation. This is the equation. Okay, so here the value of this we have to substitute, that is 1 by 3, and take out this epsilon naught out. When I take out epsilon naught out and substitute the value of gamma as 1 by 3, I'll get this equation. Okay, take the LCM and calculate this value. It's a simple mathematics. When I do that, I'll get this much. Okay, and rearranging the terms, I'll get the final Clausius-Mossotti equation. This is the Clausius-Mossotti equation. Any doubt?